everybody, we're going to finish module 11 today, so second half of module 11, page 365 in your textbook. Applying stoichiometry to solutions. Example 11.1 has two sections. We're going to do those, and then we're going to do some extra practice problems. So when you have to do on your own, so you have practiced this quite a bit, and you understand what you're doing. So the first section reads like this. A chemist wishes to make calcium carbonate, which is right here, the principal component of Tums, an antacid. So when your belly is not feeling too good, you can take these and it helps. And also in chalk, so it's also a component of chalk. By using the following reaction, it's given to you, that means it's balanced, you don't have to do anything. If the chemist mixes 50 milliliters of a 1.23 molarity sodium carbonate, so this is this compound right here, with excess of calcium hydroxide, this is your calcium hydroxide, that means if it's in excess, this one is the limiting reactant, means you're not going to run out of this one. How many grams of calcium carbonate will be produced? So this is the direct correlation, 1 to 1. This determines how much calcium carbonate you can produce. AQ is aqueous in water, that means it's a solution. This is happening inside a solution. So how do you tackle these? Let's go to the board. Let me write down the equation again so we have it present as we write these. And I'm going to explain this to you a tiny bit different than the book does it, because my brain, and I think some of your brains also work like mine, a tiny bit different than Mr. Wiles. And that way you have two examples of how to solve this, and you can pick the one that is most helpful to you. So let's write down all the information they're giving us. Okay, so this is given to us. It says pick up 50.0 milliliters. The molarity is given to us, 1.23 molarity, and they want to know how many grams we can produce, because this is the limiting reactant. So we already know that when we have molarity, okay, the equation, first of all, the equation gives you information in moles. So our recipe is in moles. So we need to know how many moles of this calcium carbonate we can produce. Once we have moles, we can translate it into grams. So we need to do stoichiometry. But we need to know how many moles are here. How many moles do we have coming in? If you remember molarity, the formula for molarity was the number of moles. In this case, going to be that sodium carbonate divided by the number of liters in that solution. So from here, I can find my number of moles. Moles for sodium carbonate equal the molarity times the number of liters present, liters of that solution. Let's find out what we're missing here. So this is what I want to find, okay? The number of moles. So I can do stoichiometry. Do I have molarity? Yeah, I do have molarity. Do I have the number of liters? No. I have milliliters. So I need to translate my milliliters into liters. Factor level method. I don't want milliliters, I want to end with liters. How are they connected? 1,000 is 1 liter. So when I do the math, I find out that I have 0.0500 liters. Do I have all the information I need now to find my moles? Yeah, I do. My molarity is 1.23 what? Moles per liter. That's what molarity is. Multiplying the liters I just found, 0.0500 liters. Liters are going to disappear, and I'm going to be left with moles. How many moles? I'll put it in the calculator. the moles, okay, the number of moles, when I put everything in the calculator, come to 0.0615 moles of that sodium carbonate. Okay. So now I have everything I need to do stoichiometry. I have translated this. Let me erase part of this so I have room to keep thinking. Okay. I have translated this information they gave me, all of these. Allow me to calculate the number of moles, 0.0615 moles of that sodium carbonate. Now that I have the amount of moles coming in, I can do stoichiometry. How are they related? 1 to 1. 1 can produce 1. So I can do stoichiometry and say 1 to 1. I'm going to write it down, but you know it's going to be the same number. Hopefully you can see the 0.0615. I'll write it down just for being more accurate, but I mean, if you multiply and divide by 1, you're not going to change anything. So what? The moles of the sodium carbonate go at the bottom. The moles of the calcium carbonate, which I'm trying to find, go at the top. How are they related? Stoichiometry, 1 to 1. So I end with 0.0615 now. Moles, this is gone. Moles of calcium carbonate. Great. So I have this right here is 0.0615 moles. I just found how many moles using stoichiometry. If I have 0.0615 moles of sodium carbonate, I produce the same amount of calcium carbonate, 1 to 1. But they don't want the number of moles, they wanted the number of grams. So I need to translate this into grams, and we know how to do that. So 0.0615 moles of the calcium carbonate. I don't want moles of calcium carbonate. What do I want? I want grams. So if you remember, if you start adding AMUs, atomic mass units, for each one of these items right here, and you call it grams, then you have 1 mole of that substance. Okay? When you 1 mole is 100.1 grams. So how did that information come? Where did it come from? So the calcium, finding the molecular mass of the calcium carbonate, I go to the periodic table, okay, and I start adding each one of them. This is a review. I'm not going to do this for each one of the problems, but for the first one, just to review your mind about how this was done. Refresh your mind. I find calcium in column 2A, and I see that it's 40.1. There's only 1 of them. I add the calcium, which is in position 6, and that's 12 AMUs. This is 1 of them. And then I add my 3 oxygens. Each oxygen is 16.0. So I multiply it by 3, put everything in the calculator, and that's the 100.1 AMUs. And remember, when I don't call it AMUs, I call it grams. I have 1 mole of that substance. So that's where it came from. But for other problems, I'm just going to be a tiny bit faster, okay? That's where it came from. You have done this over and over and over. And let's see. Let's erase this part so I have some space to write down the answer. When I put everything in my calculator, I find that I actually produce 6.16 grams of calcium carbonate, and that is my answer. So remember to put it in a little square so I can see the answer, that you got the answer correctly when you do all the on your own. Okay, so this is the first section of this example. Let's erase and do the second section. It's on page 300. Let me see. Here it is. I'm going to read it to you. Page 366. Second section says the following. How many liters, not liters, liters of 0. Let me see for a minute. Okay, I went in and corrected that. Sometimes my fingers type faster than... Anyway, how many liters of a 0.245 molarity solution of sodium chloride will be necessary to make 100 grams of aluminum chloride according to the following reaction? So the reaction is given to you. You don't need to write the reaction, and you don't have to to balance it. It's balanced for you. How do we solve this? Let me write down the information given to you, or to us. It's given to me too. Let me get some white. Here we go. So balance equation is your recipe, aqueous, water. So this is a solution. Stoichiometry of solutions. That's what we're doing. And then here we go. Copying things usually takes the longest. This is a solid. And this is a quote. Okay, so let's read it again and put the information where it belongs. It says, how many liters of 0.245 molarity solution of that sodium chloride, so this is the sodium chloride, they give us a molarity, 0.245 molarity. You want to know the liters, the amount of liters, will be necessary to make 100 grams of that aluminum chloride. So they produce, well, they want to produce 100 grams, okay, according to the following reaction. That's all the information they give you. Now remember that the equation does not give us information in grams, it's all in moles. So anytime that they give you grams, you are going to have to translate the information into moles. But let's see for a minute what we need to be doing, okay? To find the liters, this comes from molarity being the number of moles of what? Of the sodium chloride divided by the number of liters of that solution. The number of liters is going to come from this formula. So if you modify the formula to find the number of liters, you're going to have that goes on the other side multiplying. Now this goes to the right side dividing to get rid of it. That's algebra. So you're going to have the number of moles of that chloride divided by the molarity. Do we have the number of moles of that sodium chloride? No, we do not. Stoichiometry is going to help us find the number of moles. So doing stoichiometry between here and here will allow us to find the number of liters. We need to find the number of moles. We don't have that. We do have molarity. Now, let's go ahead and find the number of moles of the sodium chloride. How do I find that? I do stoichiometry. I need to know how many moles 100 grams is so I can do stoichiometry in reverse. So if I want to produce 100 grams, how many moles is that? To do those moles, how much do I need of these according to the recipe? So you work backwards. You have done this before as well. So let's do that. 100 grams of the aluminum chloride. Grams of aluminum chloride is what I don't want. What I want is moles of aluminum chloride. I know that if I start adding AMUs for this molecule, and don't call it AMUs, I have the number of grams that are in 1 mole of that substance. So start adding the atomic mass unit for aluminum and the 3 chlorides. And if you do that, you'll find out that you have 133.5 grams of aluminum chloride in 1 mole of aluminum chloride. Put everything in the calculator, and this is the equivalent to 0.7491 moles of aluminum chloride. So I'm going to put it here, 0.7491 moles. Let's make a tiny bit of room. What do I need to do next? I need to do stoichiometry. Let me put in a different color between these and these, okay? Because I need the moles of sodium chloride. If I produced 0.7491 moles of aluminum chloride, how many moles of sodium chloride I had to start with? That's what you're doing. So start with what you have, 0.7491 moles of aluminum chloride. I don't want moles of aluminum chloride. Remember, you're doing stoichiometry. I want moles of my sodium chloride. How are they related? 3 to 1. The 3 is with the sodium chloride, so find that. Put 3 here. The aluminum chloride is 1. Put the 1 there and put it in the calculator. So basically, you need to start with 2.247 moles of that sodium chloride to be able to produce that 0.7491 moles. Okay? So now I know how many moles. This is 2.247 moles. And I have this amount. I have the number of moles of sodium chloride. The molarity was given to me. So the only thing left for me to do is plug everything in the equation. Go back to yellow. So the number of liters equals the number of moles, 2.47. Sorry, I forgot to put a 2 here. 2.247 moles of what? Sodium chloride divided by the molarity. And what's molarity? 0.245 moles per liter. So the moles are going to cancel. You're going to be left with liters. If you put everything in the calculator, you find that you have 9.17 liters of the solution are needed. Okay, so the question was, how many liters of that solution will be necessary? You'll need 9.17 liters of that solution to be able to produce 100 grams of aluminum chloride. Okay, let's do more practice problems so we get to be really good at these. So 2, 3, and 4. I'm going to give you the answer, and if you do it by yourself and check the answer, if you did well, just move on. This is a video, make it useful for yourself. If not, if you cannot get to the same number, then check to see how it's done. Let's see, let me copy the answers. Let me go to number 2 first. So the answer for number 2 is 28.1 grams of aluminum carbonate. Number 3, the answer for number 3 is 0.768 moles of this compound. Let me see what else. Number 4. So we had 3 to work through. And number 4, the answer is, let's see, here it is, 6.00 times 10 to the 2 milliliters. So if you got these numbers, move on. Just keep watching the video, just speed it up. If you need to see some sections, just speed it up to the point that you need to watch. Let's start with number 2. I'm gonna solve it for you. So number 2. Let me read the problem and write all pertinent information. Your extra practice problems, remember, are on page 579. It says the following reaction is performed in the lab. Okay, it's given to you, so it's already balanced. So it is a recipe. And I'm not putting the state because I don't have a lot of room. And I usually run out of room here. So probably this is what takes the longest, is to copy these long equations, these chemical reactions. Okay, and you can see aqueous everywhere, so it's in water, it's a solution. What else do they give us? It says how many milliliters of, no, I'm reading the wrong one. Just a second. Okay, here. If 191 milliliters of a 1.25 molarity aluminum nitrate. So where's aluminum nitrate? Here. Okay. Identify that first and put 191 milliliters. They also give you the molarity, 1.25 molarity. So if you add to an excess of potassium carbonate, so basically this is not the limiting reactant, you have a lot of it, you're not going to run out of it, this limits the reaction. How many grams of aluminum carbonate will be produced? So aluminum carbonate is right here, and they want to know grams. To be able to know the grams, I need the moles, because all of this is in moles. And I need to do stoichiometry between what is given and what I want. So the first thing I need to do is, from this information right here, is find the number of moles. How many moles? Okay, come in. Well, let's do that. The number of moles equals the molarity multiplying the number of liters of that solution. Do I have molarity? Yes, it's given to me. Do I have liters of the solution? No, I had milliliters. So I need to notice that. I need to notice that I need to change that to the milliliters to the liters. So I'm going to just put the information directly in. Molarity 1.25. That's moles per liter. Remember what it means, molarity. Multiplying. I'm going to put it in parentheses so it doesn't get confusing. 191 milliliters. I don't want milliliters, I want liters, so it's 1,000 of them in 1 liter. Calculators are great with parentheses, just put everything in and you can find out how many moles you have to play with. And according to my calculations, that comes to 0.239 moles. So let me erase the question mark because we just found out how many moles were coming in. This is 0.239 moles of that aluminum nitrate. Okay, let me erase some of these so we have more room to do math. Now, are we done? No. We know the number of moles coming in, but we don't have the information that we need. We need moles. How many moles were produced? So we need to do stoichiometry between what we know and what we need. Let's do that. So what? We know that we have 0.239 moles of that aluminum nitrate coming in. I know that according to the recipe, let me copy this first. These are most two. According to the recipe, 2 of these will produce 1 of these. So find where this is. I put a 2 in front of it. So here you go. And how many moles? 1 mole up here. So do the math. Let the calculator do the math. And you can find how many moles that is. And according to the calculations I have done, 0.120 moles of aluminum carbonate can be produced. So I know now that this is 0.120 moles. Okay, let's keep going. These problems are not very complicated. You have done all of these before. They are just long, so don't get lost. Just keep going. Like, what do I have? What do I need? How do I find what I need? Just keep working. Are we done? No. We need to find the number of grams. They don't want moles. So let's translate our moles. The 0. So we want grams. 120 moles of that aluminum carbonate. I don't want moles of that aluminum carbonate. I want grams of aluminum carbonate, because that's what they were asking for. And I know that in 1 mole, if I start adding the AMUs for each one of those, so 2 aluminums, 2 carbons, and 6 oxygens, add them up. That's what the formula says. If you start adding them up, you know that in 1 mole there are 234 grams. Put everything in the calculator, and that's where that 28.1 grams of aluminum carbonate answer came from. Make sure that you have it squared, so I know where to find it when you present on your own. Okay, there you go. Number 2 is done. Let's look at number 3 now. And let me copy the formula, because number 3 says potassium cyanide can be made in the following way. So let me write down your recipe. I think I have enough room here to put the state, so I'm going to put it in. There's water, liquid, and here's your potassium cyanide. Okay. How many milliliters of a 1.51 molarity solution of, so this is what they're giving us. Here you go, 1.51 molarity. How much? They're asking for the milliliters, that's the question. Will be required to make 50 grams of that potassium cyanide. So this is also what you know. You know that you're producing 50 grams. And it says assume that there is an excess of the potassium hydroxide. So this is not the limiting reactant. This limits the reaction. So if you produce those 50, what did you start with? I need to do stoichiometry between here and here, which is a 1-to-1. So I need to know how many moles 50 grams is. Okay, because I cannot work with grams. I need moles produced to find out how many moles I needed to start with. Let's translate those 50.0 grams, the potassium cyanide. So I don't want grams of potassium cyanide. I want moles of potassium cyanide. Okay, I know that in 1 mole, if I start adding AMUs, I know how many grams are in 1 mole. So go to periodic table, find potassium and the cyanide, and start adding them up. If you do that, you'll find that 65.1 grams is the amount that you have in 1 mole. Put everything in the calculator, and you get 0.768 moles of potassium cyanide. So now we know that this is 0.768 moles. Great. We have moles now. Now we can do reverse stoichiometry. So basically what you're saying is these moles is what I want to be able to produce this. How many moles did I have to start with of the reactant? it's 1 to 1. Okay, it's 1 to 1. So basically, it's the same amount. I can put it down so you can see it, but anytime you have 1 to 1, nothing is going to change. So you start with 0.768 moles of that potassium cyanide. I don't want moles of the potassium cyanide. I want moles of this acid. So 1 to 1 will not change anything. Multiply by 1 divided by 1. So 0.768 moles. But now you have changed the units. You have moles of the acid here. Okay. So now we know that this is 0.68 moles. Okay. Perfect. Now what? We know now the number of moles. We know the molarity. That means that we can find out the liters, because molarity equals the number of moles of whatever we're talking about. In this case, is this acid divided by the number of liters. We're going to have to change it to milliliters because the question is how many milliliters. From here, we're going to find the liters. So the number of liters is going to be the number of moles divided by the molarity. So put all the information in because we have all the information. Moles, 0.768 moles. Molarity, 1.51 moles per liter. Moles are gone, you're left with liters, and if you do the math, that is the same as 0.509 liters. We're not done yet because they didn't want liters. Okay, we need to change this into, I'm going to put another color. What color? Okay, 9. I need to change, oh sorry, red, come on. The mouse doesn't want to work sometimes. 0.509 liters of that acid. I don't want liters of the acid. I want milliliters. Well, I know that in 1 liter there are 1,000 milliliters. So when I do that, I'm gonna erase that question mark because I put everything in the calculator, and then I get the following number: 509 milliliters of that acid. And you're done. So keep thinking, what do they give me? What do I need? What formula allows me to calculate that? And keep filling the blank, just one step at a time. Don't get lost in the process. Just keep thinking, this is what I have, this is what I need, how do I find it? And the last one, number 4, reads like this. Let's see. When a copper is mixed with nitric acid, the following reaction occurs. Okay. Let me copy. That's your solid. Sorry, N8 hydrochloric acid. If I don't copy those moles correctly, I don't have a recipe. I have a mess. Okay. In water to yield copper nitrate. Okay. What else? And the last one for waters. Let me make sure that I copied right. 3, 8, 3, 2, and 4. Yeah, always check your work, because we all make mistakes. It says, how many milliliters of a 3.50 molarity solution of that acid? So here it is. They're asking for milliliters again. They give us the molarity, 3.50 molarity. Will be required to completely use up 50 grams of solid copper in this reaction. So they give us the other reactant here, 50 grams. So basically they're asking how many milliliters of this other reactant you need to complete the reaction. It doesn't matter what side of the equation, reactant or product, the stoichiometry goes back and forth. It doesn't matter. It gives you information about all of the players here. So you need to connect 3 with the 8. That's what you're going to be doing. Okay? Now what? Well, I cannot do that yet because I have information in grams. I have 50 grams coming in. I need to know how many moles are coming in. Let's find out. 50.0 grams of copper. Well, I don't want grams of copper. I want moles of copper. It's pretty nice that is only one element, so you go to the periodic table and find the AMUs for that copper, and you'll find out that, let me see my notes here, in 1 mole of copper you have 63.5 grams of copper. So I had 50 to start with, and when I do the math, I know now that I have 0.787 moles of copper coming in. This is the same. It's equivalent to 0.787 moles. Great. Now that I have moles, I can do stoichiometry. Stoichiometry between whom? The copper and that acid here. Okay? So let's do that. Start with the moles. You always start with whatever they give you. So this you found out, but it was given to you at the start in grams. You translate it to moles, and now you can do stoichiometry. 0.787 moles of copper. I don't want moles of copper. I want what? I want moles of that acid. Okay? According to my reaction here, my recipe, 3 to 8. That's how they are related to one another. If I do the math, I find that I actually can produce. Well, I'm gonna need 2.10 moles of that acid to react with the copper that was given to me. Okay? Great. So I know that this is 2.10 moles. Now, the question was, how many milliliters do I need? Let me get red. Remember, the molarity is the number of moles divided by the number of liters. From the liters, I'll be able to find the milliliters. From here, I know that the number of liters equals the molarity, the moles, divided by the molarity. Okay? So let's plug in the information, because you do know now the number of moles, 2.10 moles. And the molarity was given to you, 3.50, which is moles per liter. Plug it in, and you find that you have you need 0.066 liters of that acid. Okay? And then what? Well, you're not done yet, because they don't want liters, they want it in milliliters. So translate that. 1 to 1,000. Multiply by 1,000, you find out how many milliliters of that acid you needed to react with the 50 grams of the copper. Okay? Another way to think about this is, I need the milliliters. Where are they going to come from? Well, the only way for me to find those milliliters is if I first find those liters. And that liters found when I change my molarity equation, and from there I can find liters that I can later translate into milliliters. But when you do that, you find out that you still need moles. I don't have moles, so what do I do? Well, find out how many moles. What do they give me? Grams. Translate to moles. Then I can do stoichiometry to find the moles here. So keep reasoning through. This is what I need. This is what I need to do to find what I need. Am I missing something? Yeah, I'm still missing this piece. Go find it. What do they give me so I can find that? And keep breaking every single step until you find what they ask you. And this one is solved as well. ask me questions on Friday when we do our Zoom session together. Okay? If you have questions about this. But you've been doing stoichiometry for a while, just now you're applying it to solutions. Now, molality, page 367. I told you, I think it was 2 weeks ago, don't confuse molality with molarity, okay? So molality with an L is a different thing. It's a different unit. Molarity, you've been doing molarity, the capital M, was the moles of a solute divided by the liters of a solution. We've been working with molarity. Now, molality with a lowercase m is the moles of solute, so that has not changed. But look at the bottom. Is the mass of solvent in kilograms. So not kilograms of the solution, kilograms of the solvent. Do not get confused, please. We're on page 367, and you need to know both equations and be able to modify them to find what you need from those equations. But we're going to practice. We're going to practice this. Okay? Now, how do we solve things with molality? Page 368, example 11.2. 2 sections. A chemist mixes 3.4 moles of sodium chloride with 4.5 kilograms of water. What is the molality of the resulting solution? So this is a plug-in. Number 2, if a solution is made by adding 45.0 grams of zinc chloride to 150 grams of water, what is the molality? This is one you're going to have to do a little bit more math, but not complicated yet, okay? And then we're going to do extra practice problems 5 and 6. Let's start with the first section of this example. Okay, so they say a chemist mixes, let me get the pen. Okay, so we're doing example 11.2, okay? And that's on page 368. So a chemist mixes 3.4 moles of sodium chloride with 4.5 kilograms of water. They're mixed, so you're creating a solution. What is the molality? Remember what molality was. Molality is the number of moles of the solute divided by the number of kilograms of the solvent. Do we have all the information? Well, yeah, the solute is your sodium chloride, your solvent is your water, and is in kilograms and moles. So plug it in. 3.4 moles of the sodium chloride divided by 4.5 kilograms of water, H2O. Do the math, and you get 0.76 molality. So moles of the solute divided by kilograms of the solvent. You just put molality, but remember what molality means, because sometimes you're going to have to change between units, writing it like a little m, lowercase m, or moles of solute by kilograms of the solvent. And this is your answer. This was a plug-in. Plug it into the equation. Let's do the second section. If a solution is made by adding, okay, what are you adding? 45.0 grams of the zinc chloride to 150 grams of water. What is the molality? Well, molality equals number of moles of what? The solute. Who is the solute here? The zinc chloride, divided by the number of kilograms of the solvent. Who is the solvent? The water. Well, the universal solvent, water. Do we have moles and do we have kilograms? No, we don't. But we can find out. Well, translate those grams into moles. Grams of zinc chloride at the bottom. I want to end with moles of zinc chloride. I go to my periodic table and I start adding AMUs. and I know how many grams are in a mole, and that is 136.4, meaning when I do my math that I have 0.330 moles of my solute. So I have the first section done, 0.330 moles of that zinc chloride. Okay. Well, they gave me grams and I need kilograms. So I don't want grams, I want kilograms of water. I know that in 1 kilogram I have 1,000 grams. So I put it in my calculator and I find out that I actually have 0.1500 kilograms of water. So now I can put that at the bottom of my equation, 0.150 kilograms of water. I can do the math in my calculator and find that I have 2.20 moles of my solute divided by kilograms of my solvent, which is water. But I can also call it lowercase m, 2.20 m, because that m means that solute, moles of solute divided by kilograms of the solvent. And that is my molality. And I'm done. Let's do a tiny bit more. The more you practice, the better you get at this. So let me give you just the answer and just do the same thing as before. Got the answer correct, move on. If not, try again if you want to, or check to see how it's done. So number 5 and number 6. These are the answers you should get. Always pause and try on your own. Let me get my answers so I don't tell you a lie. So number 5 is 0.674 molality, and number 6 is let me see, 28 grams of that calcium chloride. Okay, so these are your answers. Let's see how we solve this. Start with number 5. This is the video, make it work for you. Stop when you need to stop. Rewatch it if you need to rewatch it. Skip if you need to skip. So what does it say, number 5? What does this problem say? It says, what is the molality of a solution? So we want to know the molality in which 50.0 grams of magnesium nitrate are dissolved in 500 grams of water. Okay, well, remember what molality is. Molality equals the number of moles of our solute. What is solute here? The magnesium nitrate divided by the number of kilograms of our solvent, which is water. Do we have what we need? Do we have it? Do we have moles? No, we have grams. Do we have kilograms of the water? No, we have grams. So we need to find those first before we can plug anything in. I don't want grams of my magnesium nitrate. I want moles of my magnesium nitrate. I know that in 1 mole, if I add the AMUs and call them grams, I know how many grams are in 1 mole. I do that. I go to the periodic table, excuse me, I add my magnesium, add 2 nitrogens and 6 oxygens together, and find out that 148.3 grams is 1 mole. And when I do the math, I'm going to put it here, I have 0.337 moles of that magnesium nitrate. And I'm sorry, but yeah, maybe I can put it like this, more or less. You can see what it is. Okay, great. I'm not done yet. I need to translate my water grams into kilograms. So no more grams, I want kilograms. 1,000 grams in 1 kilogram. Do the math, and I'm going to put it at the bottom here directly already. I have 0.5000 kilograms of water. When I do the math, see. Let me put, oops. Okay. Let's see. When I do the math, the calculator says that I have a molality of 0.674 molality. And remember what molality means. Moles of magnesium nitrate divided by kilograms of water. That's what it is. That's your molality. And you're done with that problem. So number 6. So we're doing number 6. For number 6, it reads like this. How many grams, so they want to know the number of grams, of the calcium chloride would you have to add to 125 grams of water to make a solution with a concentration of molality. So this is not a unit of concentration. Molality and molarity both are concentration units. So this molality is 2.0 molality. Okay? So you're working backwards. To find the number of grams, you need to first know the number of kilograms. You find the number of kilograms from the molality, because if you remember molality, that's the number of moles of your solute. Who is the solute here? The calcium chloride. Actually, you need moles to find this, because you're not trying to find the solvent, you're trying to find the solute. And divided by the number of kilograms of your solvent, which is the water. From here, I can find the moles of calcium chloride, and once I have moles, I can translate that into grams. So let's modify this formula. I want to have the number of moles of calcium chloride. So that is my molality multiplying my number of kilograms of the solvent, which is water. Do I have molality? Yes. Do I have kilograms of water? No. I have grams of water. So the first step is translate this into kilograms. So grams to kilograms. 1,000 of them in 1 kilogram. And if I do that, I get, let's see. I think I did it directly. Okay, I did it directly in my notebook. So let me erase this and see and show you what I mean by directly. It's like I don't have a calculator right now, but the number of moles we said of the calcium chloride is going to be the molality, which we do have 2.0 moles. Moles of the calcium chloride divided by kilograms of water. That's what it means, molality. I'm translating it already. And then I put this right there. So 125 grams, 1,000 dividing at the bottom, 1 at the top. And then the grams are gone, and I'm going to be left with kilograms. The kilograms are going to be gone too, and then I'm going to be left with the moles. That's what I do. That's what I do. I put it directly in the calculator, and that way I don't have little steps in the middle. But you can break it apart into steps. You always can do that. But when you do that, the calculator gives you 0.25 moles of that calcium chloride. Are we done? No. We do have the number of moles, but not the number of grams. And the question was, how many grams? So let's see. I'm going to put that number up here so I can make some room. I have moles now of the calcium chloride. I need to translate moles into grams. And you know how to do that. You know how to do that. Start with the moles. Open your factorial method. Say, I don't want moles anymore. I want grams of that calcium chloride. I know that in 1 mole, if I add the AMUs for each one of the atoms in that molecule, I'll know how many grams are in 1 mole. If I do that, I see that I have 101.1 grams. The moles now are gone. I'm going to be left with grams. Multiply divided by 1, I get 28 grams of that calcium chloride. There you go. You're done with this extra practice problem. Now, I'm going to erase this. See, what else do we need to do? There's a lot of math. Last week we didn't have any math. This week we have a lot of math. You had to do experiments. Well, this week you also will do this experiment. It's freezing point depression. So basically we're going to talk about freezing point depression in a minute. But you are going to do an experiment that shows how freezing point depression works. And we're going to talk about it during our Zoom meeting before we turn it in. But of course, you always can ask me questions during the week if you have any questions for me. What is a freezing point depression? Well, is the depression, so the lowering of the temperature, the freezing temperature, due to adding a solute into a solvent. So when you add a solute into a solvent, the freezing of that solution that now has the solute in it will decrease. Page 370. Just keep along. There's a formula that allows you to find out by how much it goes down, the freezing point depression. Delta means the difference in temperature equals minus, because it's lowering. I is the number of molecules or ions the solute splits into when dissolved. So if you have an ionic compound, how many ions does it break into? If it's a polar covalent, it's going to be 1, because they don't break into little parts. They stay as a molecule. Kf is a constant, is the freezing point depression constant, and it depends on the solvent. It's going to be given to you. And then lowercase m, you know what that means. That's molality of the solution, which is the number of moles of the solute divided by the kilograms of the solvent. So by using this formula right here, you can find out by how much does the freezing of that solution, by how much does it lower once you add a solute to a solvent. The freezing point lowers because you added that solute in. By how much? Use the formula and you can find out. We're going to see some problems in a minute applying this formula. Why? You also need to know not only how to use the formula, but also explain why adding a solute lowers the freezing point. Why does that happen? As the substance cools, okay, what happens? It loses energy. Remember, you go from a gas to liquid by taking away energy in the form of heat. From liquid to a solid, which is a frozen water, for example, is a solid, okay? So you're going to a solid state. You keep losing energy. As it loses energy, all the atoms and molecules in there start to slow down. That's what happens before you turn into a solid. They vibrate a tiny bit, but they're not moving very much. They don't have a lot of energy. They get closer together. Solid. When a solute is dissolved in a solvent, so now you're adding something in it. You're adding more molecules or ions if you have ionic compounds. Then they start moving around in the solution. You create a solution. When that happens, when those molecules are moving around, it's like they're chasing one another, and that adds energy to the solution. The movement of those particles translates into energy. So to freeze now that mixture that you created by adding the solute, you have to lower the temperature by a certain amount to compensate for all this movement created by the molecules and ions that you put in there. To slow down and stop them, more energy must be removed. When you remove energy, one way to do that is by lowering the temperature of freezing. How do we apply this to problems? Okay, so not only do you need to know why is it happening. Let me see. I'm trying to make this small so we can read that a little bit better, but it doesn't look like it's gonna do it. Come on. Now. Yeah, there you go. But we need to apply that formula that we just learned. Page 371. Example 11.3. It has 3 sections, and then I have 3 problems for you, extra practice problems. Lots of practice today. First, when 15 grams of sodium chloride are added to 100 grams of water, what is the change in the water's freezing point? And they give you the constant freezing constant for water is given to you. That's always going to be given to you. And you don't have to memorize them. Number 2, what is the freezing point of a solution that is made by mixing 2.5 grams of aluminum nitrate to 150 grams of water? Constant of the freezing water is always the same, is given to you. Number 3, what is the freezing point of a solution that is made by dissolving 100 grams of table sugar, is given to you, the formula, into 950 grams of water? Constant for freezing for water, given to you. Let's break this down and see how this is done. Okay, section 1. So we're doing example 11.3, and this is on page 371. Everybody follow along. It says when we have 15.0 grams of sodium chloride, 100 grams of water, what is the change in the water's freezing point? So change in freezing point, this is the formula. So what does the formula say? It says that the temperature will decrease. By how much? That's what we need to try to figure it out. Okay, F and the molality. Okay. Let me see. KF of water, that was given to me too. I should have written this down. Of water. I put water like this. 1.86.0 degrees Celsius, and this is your molality. Okay, and this is the formula which you're gonna have to memorize. That's all they are giving you. This is all you have. Let's play with this. Do I have I? I, if you remember the definition of I, is the number of ions an ionic compound breaks into, or the number of molecules if it's a polar covalent molecule. And it's going to be 1 because it doesn't break into ions. So the first thing we need to do is find I. I have an ionic compound. This breaks into sodium and into chlorine ions. That makes my I 2, because I have to count how many ions this breaks into. 2 ions, I equals 2. Great, I have I. Do I have KF? Yes, that was given to me. Do I have molality? I don't see molality here anywhere. I need to find molality. Okay. What is that? Well, the number of moles of my solute, and here is your salt. Remember that. That's your salt. Divided by the number of kilograms for my solvent, which is water. Great. Do I have the number of moles for the sodium chloride? No, I have grams, but I know how to translate this into grams. I'm gonna put it directly up here. Well, 150 grams of sodium chloride. I don't want grams of sodium chloride. I want moles of sodium chloride. So I know how to find how many grams are in 1 mole. I just go ahead and start adding the AMUs for each one of the atoms. So 58.5 grams in 1 mole. Grams are gone. Now I do have moles. Now, do I have kilograms of water? No, they give me grams, but I know how to change that. 100 grams of water. 1,000 grams are in 1 kilogram. I don't have grams now anymore. I have kilograms of water. You can break each step, the top and the bottom, into 2 different steps if you want to, or you can put everything in your calculator, and then you'll find out that you have 2.56 molality. So now I have everything I need. I'm gonna put my molality here. I just found this 2.56 molality. I can plug all the information now into the formula they gave me. Well, The change in the temperature. Temperature when you freeze by adding a solute into it goes down. That's why you put salt on the roads. So it needs a lower temperature to freeze. Negative. I, what was I? 2. What was Kf? 1.86 degrees Celsius divided by molality. Multiplying the molality we just found, 2.56 molality. This is gone. And you're going to be putting everything in the calculator and ending with Celsius. How many? Minus 9.53 degrees Celsius, the change of temperature. So freezing for this water that you just added salt to this water needs to be 9.53 degrees lower than the freezing temperature of the water. So minus 953 degrees Celsius. Okay? You need to write this down because it says what you need to do. The answer means that the freezing point of the sodium chloride solution is 9.53 degrees Celsius lower than the normal freezing point of water, which is 0 degrees Celsius. And now you have solved the first section of this example. Second section. What is the freezing point that is made by mixing? So they want to know the freezing point. I'm trying to find out. Okay. You have 2.5 grams of aluminum nitrate. So and 150 grams of water. That's your solvent. They give you the Kf for water, constant for freezing. And what are they asking for? They're asking for the freezing point of a solution. So what temperature? That's what they're asking. They're asking for these. Okay? So formula, write it down and see what you have and what you still need. You have I. Well, let's look at the solute. The solute is an ionic compound. Break it apart. What do you have here? You have one of these. And how many of these do you have? You have 3. You see that? Meaning that your I equals 4. So you have to count into how many ions your ionic compounds break into. You have I. You have Kf. You have molality. No, but once again, it's just like before. You can find out the molality. The molality is the number of moles. Moles of what? Of your solute. So of that aluminum nitrate divided by the number of kilograms of your solvent. Who's your solvent? Your water. Let's put all the information in already. I have grams, so I need to translate my grams into moles. I don't want grams of aluminum nitrate. I want moles. And if I start adding AMUs, I know how many grams are in 1 mole. And that is 213.0 grams. Now, do I have kilograms? No, they give me grams, so I'm going to have to translate that 2 into the right units. I know 1,000 grams are in 1 kilogram of water. I'm talking about water. So this is gone. Let's see, the grams here are gone, and you're going to be moles of the solute divided by the kilograms of the solvent gives you molality. So do the math, put everything in the calculator, and your molality comes up to 0.080 molality. So I'm going to put it up here so I have all the information together. 0.80 molality. Am I done? Oops, I clear it up. Let me write this down again then. Well, I was 4. Molality was 0.080 molality. My formula looked like this. And I also had the KF, because that's not changed for the water. It's 1.86 degrees Celsius per molality. Okay, I have everything now to plug in. All the information is up there. So put it in. Minus what? 4 KF, 1.86 degrees Celsius divided by molality, multiplying the molality that we found, 0.080 molality. And if you do this, you find out that the temperature decreased by 0.60 degrees Celsius. So by adding aluminum nitrate in the water, the freezing temperature went down 0.60 degrees Celsius. That's what it means. Great. Now we can erase. Third section of this example. Third section. Let's see. What is the freezing point of a solution? So once again, they're asking for the freezing point. So that's the formula that we need to use. And what do they give us? We're dissolving 100 grams of sugar, and they give you the molecule: 12 carbons, 22 hydrogens, and 11 oxygens. They're dissolving this in 950 grams of water, so that's your solvent, and they give you the KF for water, which is 1.86 degrees Celsius divided by molality. Okay, let's look at the formula. I'm given to you, no, but you can find out. Because you know the molecule, this is not an ionic compound. It is not. This is a polar covalent compound. Remember that when polar covalent compounds get dissolved in water, the whole molecule is surrounded by water. They just break into molecules. How many molecules? I equals 1. It doesn't break into parts. This is a whole. You need to remember that all of the polar covalent compounds, I is going to equal 1, because the molecule stays together. Doesn't break down into smaller particles. Do we have KF? Yes. Do we have molality? No. We can find the molality. We've been doing this all along. Number of moles of my solute. Just use sugar. Divide by the number of kilograms of my solvent, just water. Well, find out. Moles, 100 grams. I don't want grams. I want moles of sugar. And I know that in 1 mole, if I start adding the AMU, so 12 carbons, 22 hydrogens, and 11 oxygens, my total comes up to 342.2 grams for 1 molecule of sugar. The grams are gone. I'm going to be left with moles of sugar. And do I have kilograms of water? No. I have 950 grams. I need to be translated in 2 kilograms. Grams to kilograms, 1,000 to 1. So grams are gone. And now I have the right units. 0.31 molality is my molality. Now we can plug everything in. Minus, well, 1 multiplying what? 1.86 degrees Celsius molality, and the molality I just calculated, 0.31 molality. Units work out perfectly. And the temperature, the depression in the water, temperature is minus 0.58 degrees Celsius. So by adding sugar to the water, the freezing temperature went down 0.58 degrees. Okay, this is done. Now we're going to do some more. Okay, I'm going to give you first the answers for number 7, number 8, and number 9. And once again, use this for your benefit. If you need to see how it's done, watch it. If you know how to do it, move on. So the answers for number 6, 8, and 7. Let me get that. Not 6, 8. 7, 8, and 9. I mean 7. Okay. 7, 7, 7. Let's see. What are they asking? Number 7 is a tiny bit tricky because it is asking which one would work better. The one that's going to work better is the one that has the highest I. And that is going to be this compound. I'll explain to you in more detail in a minute when we work through it. But if you got it, you got it. If not, try again or check to see why. Let's see. Number 8, the depression here is minus 6.40 degrees Celsius. And for number 9, they wanted the molality. You have 0.896 molality. Let's break down each one. Number 7. So let me read number 7. So we're doing number 7 here. It says, if you wanted to protect water from freezing, which compound would accomplish this the best? And they give you the compounds. So this is what is given to you. PO4, here's another one. Aluminum nitrate. And sodium chloride. It says, assume the molality of the solution is the same in each case. So they're saying that the molality is the same for everybody. This is not a factor. The Kf of water is the same for all 3 of them. So this is not a factor. We need to find out which one will lower the temperature the most. So which one will have the highest I, the number of ions it breaks into. Because the larger this number, the lower the temperature is going to be. So let's try to break down these ionic compounds into the components, the ionic components. What do we have here? We have calcium. How many? 3. So this one is 3. How many of these PO4? It says 2. So add them up. This is an I of 5. What about this one? It says aluminum times 1 is only 1. I put in parentheses too. And NO3 is how many does it say it has? 3. That gives you an I of 4. Sodium chloride. Well, this is the sodium and this is the chloride. 1 each. So that's a 2. This one has the highest I, making this the compound you want to use. So if you want to protect water from freezing, you want to lower the temperature at which it freezes, and the one that's going to do the best job to do that is the one that has the higher I, the number of particles it breaks into. That's it. That's how you do that. And now let me erase these. Moving on to number 8. And if you have questions, ask. But you're going to have some on your own to do that are similar to these. So pay attention, please. So what is the freezing point of a solution that is made by dissolving 10 grams of that potassium fluoride and 100 grams of water? You've been doing this kind of problem, so it should not be too complicated. They want the change in temperature. Write your formula. Okay, F is done, that's given to you, times your molality. Okay, that's an ugly M, but it's an M. Okay, that's a formula that will allow you to do that. So see what they are giving you. It says 10 grams of your solute. Oops. Oh my goodness. Okay, KF. And 100 grams of water. Do I have I? I can find I. Is this ionic or not ionic? That's the first thing you need to do. You need to decide into how many it will split. Well, the I for this, being an ionic compound, is going to be 2. It's opposing to the potassium and the fluoride. So I equals 2. Once you have done that, once you have decided the I, you need to find the molality, because Kf is always the same. Kf, sorry, I should have written it this. The problem gives it to you. Kf for water equals 1.86 degrees Celsius per molality. So that's given to you. And we have a problem because molality is the number of moles of our solute, so that Kf divided by the number of kilograms of our solvent, water, and we don't have either. But we know how to find that. We've been doing this all along. You can do it directly or separate, but grams of Kf can be translated into moles. Kf grams moles of Kf, and you do that by going to the periodic table and saying in 1 mole how many grams do we have. So add them up, and my adding up is 58.1 grams for mole of Kf. Now water is not given in kilograms either, so I need to translate that as well. No grams, I want kilograms. So grams of water, kilograms of water. This is gone. Now I'm left with kilograms, and it's 1 to 1,000. If I plot all of these in the calculator, I can find my M. And my M, my molality, is 1.72. So now I have all the information that I need. Okay, I do have all the information to plug in. It's a plug in directly, and that's where that minus 6.40 comes from. I'm not going to plug it in. Just put I2, Kf 1.86, M 1.72. And you'll get that negative 6.40 degrees Celsius. Now, 9. Let's read it. Half the job is just reading and understanding what they give you, what they're asking. If you want to lower the water freezing point 5 degrees, so you want the change of temperature to be 5 degrees. That's what it means, okay? You want to go to minus 5 degrees because water freezes at 0 degrees. And you want to do that by adding this solute, calcium chloride. What must be the molality of that salt solution? So what is the molality? And you're doing it in water, so you know that the Kf for water equals 1.86 degrees Celsius per molality. Well, what's the molality? Molality means what? Number of moles of what? The calcium chloride divided by number of kilograms of water. Okay? Okay. Let me get my notes right here. See, what are they giving us? They give us these. What does that mean? What's AT? Write the formula first to see what you have and what you need. Kf and molality. Okay. This is given to us. There you go. Kf is given to us. And the molality is what we need. So we don't need this formula right here. From this formula, we can find the molality that we need. So let's do that. Thinking and reasoning, one step at a time. Okay? So molality. Molality is the change of temperature, and everything that is multiplying on this side is going to go on the other side, dividing. So minus I times Kf. Do I have the change in temperature? Yes. It was minus 5.00 degrees Celsius. It was lower than the temperature of freezing water, which is 0. So that's a negative number. The negative is here. What is the I? Oh, we need to find the I. Well, here is my compound. 1 calcium, 2 chlorines. So that's my 3. I is 3. Kf was given to me 1.86 degrees Celsius divided by my molality. Well, this is going to be gone, and you're going to be left with units of molality. Put everything in the calculator, and you find that your molality is 0.896 little lowercase m, which means moles of calcium chloride divided by kilograms of water. There you go. So if you wrote the other equation, you would have noticed that you were missing a lot of things. And then you would think, okay, what other formula can give me molality when I have a change in temperature due to adding a solute? Well, the freezing point depression equation. You can find the molality from there. Okay? So one step at a time. Let's move on to the last section of this module. The same way that you could calculate the freezing point, so lowering of the freezing point due to the addition of a solute, there's also what's called the boiling point elevation, meaning that a solvent's boiling point will increase by adding a solute. So temperatures decrease for freezing, temperatures increase when boiling when you add a solute. So adding a solute changes both the freezing point and the boiling point of the solvent. Freezing point goes down, boiling point goes up. Page 374. You have a new formula. The change in the temperature is increasing, so that's why it's a positive number. Is I still the same, meaning break down those ionic compounds, but if it's a polar covalent molecule, that's 1. And then you have a constant that's going to be given to you, a boiling constant for the solvent, and the molality again. We're working with molality again. Why? Why does the boiling point goes up when you add a solute? So water with salt to cook pasta, that water that's boiling, if you see the bubbles here, I mean this boiling, it's not at 100 degrees, it's at a higher temperature. So the pasta will cook faster. When you are boiling a substance, going from a liquid to a gas, you are trying to pull the molecules of the solvent apart. When you add a solute, the molecules of solvent are now attached to the solute, making it harder for the solute to evaporate. And increasing the temperature helps. Okay? So that's why you need to know the formula and the reason why there's a boiling point elevation. Apply the formula to problems. Example 11.4, page 374. Let's see. In cooking pasta, a chef adds 20 grams of table salt to 1.45 kilograms of water and brings the water to a boil. What is the temperature of this boiling solution? And they give you the constant for boiling of water. It's the same reasoning that you did for the freezing point, just you have a new formula to solve these. Now we're going to do extra practice problem number 10. So let's see. Let's write down the formula. Formula is the change in temperature because you added that solute in. It's going to be positive, it's going to go up. It's positive I, multiplying by the constant of boiling point, in this case water, and the molality for that solution you created. What else do we have? 20 grams of table salt. That's your solute. Table salt. What else do you have? You have the formula, NaCl. And 1.45 kilograms of water. That's your solvent. brings the water to a boil. Great. What is the temperature of this boiling solution? And they give you the kb for water. The constant of boiling for water is 0.512 degrees Celsius per molality. Do we have what we need? Let's see. I is not given to you, but you know what your solute is, so you can find I. kb is given to you, yeah, and the m, it's not given to you. You have to find it. Well, let's find I first. This is ionic. It breaks in two ions. How many? Two. Because it's sodium and chlorine, 2 ions. And we need to find that molality. What is molality? Number of moles of our table salt divided by the number of kilograms of our solvent, which is water. I can find these because I know that I can translate my grams. I have kilograms already, so that's not going to need to be translated. But my grams are not moles, so I need to translate that. 20 times the grams here. I should have put the formula. 1 mole. 1 mole. So how many grams are in 1 mole of that table salt? We go to the periodic table, add sodium, add chloride, the atomic mass units for each, and you find out that is 58.5 grams. This is gone, and now I'm left with moles. And the kilograms were given, so great. I don't even have to do that step. Put everything in the calculator, and you'll find out that the molality here is 0.2. 0.2 molality. Now I can plug everything into the formula. I is 2. kb was given to me. 0.512 degrees Celsius divided by molality, and the molality I found out by myself. So that's my molality. Units are going to work out, and 100.2 degrees Celsius is my answer. So basically, the temperature went up by 0.002, okay, because water boils at 100 degrees Celsius. But now this one is boiling at a higher temperature because you added salt. Not a lot, 20 grams of table salt. And that concludes that example. But we're going to do one more. We're going to do number 10. I'll give you the answer first. And once again, you get it right, just move on. Let's see. The answer for number 10 is 103.0 degrees Celsius. How did we get here? Let me read it. Okay, what is the boiling point? So they're asking for this. Here's the formula, Kb and m. Of a solution by mixing 100 grams. You don't want to eat these. And 750 grams of water. Okay. Do I have I? No, but can I find it? Yes, I sure can. Let's find I first. Did I forget to put a 2 in here? Yeah, okay. Be careful when you copy these, because that could affect your I. So what is I? According to this formula, excuse me, I right here is 2 of these and 1 of these. That makes my I be 3. In parentheses, there are 2 of them and 1 of these, 3. I have these, I have these. Kv is always given to you. Kv equals 0.5. That's given to me a minute ago. 2 degrees Celsius. So that's given to me. I don't have the molality, but I have a way to find molality. Molality equals the number of moles of what? Solute. What is the solute here? That molecule that we just split into ions. The kilograms of water or solvent go at the bottom. In this case it's water. And I need to check to see if the units are correct. Can I find moles? I have grams. I can translate that into moles, no problem. Grams, I can go into kilograms. Yeah, I can do that. So let's do it. I'm gonna erase this to calculate molality. Okay. 100 grams. I go my periodic table and I find that 68.2 grams. Ammonium sulfate is how many grams are in 1 mole of that substance. Okay, if I do that, I have 1.47 moles. Okay, I just found the moles. I'm gonna divide this by the number of kilograms. I have 750.0 grams. 1,000 grams of water equals 1 kilogram of water. This was grams of water. So this is basically 0.7500 kilograms of water. You could have done it directly. You could have done this directly, put everything in the calculator, and you would have the same answer, which is a molality of 1.96 m. Am I done? No. Now I have to plug all of these into that formula that we had at the beginning. So I'm going to put it directly already in. We calculated I to be 3. The constant for boiling for water was given to us, 0.512 degrees Celsius divided by molality. We calculated molality to be 1.96. The units work out fine, and I see that my change in temperature is 3.01 degrees Celsius. Well, it went up this amount. Water boils at 100 degrees. Add 100 to this, and then you get that 100. Let's see if I can write it down someplace. Maybe here. 103.0 degrees Celsius is your answer, because you needed to add it to the boiling point of water. That was the only tricky part. Just remembering the water boils at 100, but this is elevation. So how much it went up? It went up 3 degrees, so it's boiling at 103.0 degrees Celsius. And that completes your extra practice problem. You have done lots of problems. The module finished with 2 new terms, suspensions and colloids. You need to know what it means. Suspensions and colloids are not solutions. What is suspension then? Well, the particles are so large that they settle out of the solvent if not constantly stirred. And particles can be filtered out pretty easily because they are so large. An example, oil and water. What's a colloid? Well, the particles intermediate in size between those of the suspension. The main suspensions, they are surrounded by the solvent, and they're very tiny. And those of a solution. Particles, sorry, the solution is the one that has the small particles. The suspension is the one that has them really big. So, and they would precipitate if you don't stir them. So colloid is in between them. The size of the particles are in between. The particles cannot be easily filtered out. And an example is milk. So you need to be able to give the definition and give an example of each. And this is just a summary of this module. Factors that affect solubility. So how much solute you can dissolve in 100 grams of a solvent. Temperature, pressure, and polarity. Remember that polar, anything that has charges attracts one another. So polar dissolves in polar and ionic dissolve in polar compounds. If there is attraction, it has to be strong enough. If it's not strong enough, it will not dissolve. But for right now, know that the polar dissolves polar, non-polar dissolves non-polar. You already learned about the pressure. It does not affect solids and liquids, it affects gases. How? Pressure goes up, then the solubility of the gases also go up. And vice versa. If the pressure goes down, the solubility of the gas will go down. And temperature affects mostly the solids and the gases. It does not affect liquids very much. For solids, if the temperature goes up, the solubility of the solid also will go up, because you're giving energy to the solvent to break those solids apart. And gases react opposite to what the solids did. If the temperature went up, the solubility of that gas went down, because you're giving energy to the gas to float away. All of this has been explained, but this is a summary. It's a summary, and you need to know how this works. And this concludes this module. So read your textbook. Review examples if you need to. This is a video. You can watch it as many times as you need to. Work through all on your own as you encounter them, and correct them as you go. Study for your quiz. Do the lab that's assigned this week. You have review questions and practice problems. So I'll see you on Friday. Bye-bye.